Well, good morning, folks. Maybe I shouldn't be starting this right now. I'm really low on my coffee. I'm not even awake yet. I'm like, ugh. Got some major discoveries to share on the vortices going around the Earth. And it looks like Sagittalus vortex is actually the oldest vortex scored into Earth's crust. And, have to readjust theories on how recent was in terms of um, the South China Sea impactor striking the Earth really recent, so recent as to have been within the last 9 Jupiterian 9 stripe period. So as it begins to look, it looks like the Jupiterian 9 stripe period has been around for a really long time. What does that mean? That means that it's actually more stable than I previously thought, which is a good thing for us. Not for the planet, because we're just like infesting the planet, but good for humanity. And anywho, apparently all those great big impactors are more like what would have been expected, so they didn't happen over the course of throughout the 4.4 billion so many years. It all pretty much clobbered the planet very early on, and basically the oldest stone we found in Australia that we dated to be 4.4 billion years old. That means that the Guacanayabo impactor struck the Earth 4.4 billion years ago. And when it struck the Earth was all, relatively pretty much wholly solidified, and but probably the planetary suture had not been solidified yet. In fact, what I'm going to be doing, the research that I did here yesterday, shows that the Sagittalus vortex period, when the Sagittalus vortex was active, the planetary suture would not have been sealed, and it was sealed during that period. I was thinking it had more to do with the time when Africa precipitated, and I was thinking Africa precipitated at the time that the vortex that the vortical perimeter that I was able to identify would have reached Africa, and when I say precipitated, I've learned that from observing the sun that the continents did not migrate; they precipitated, just like the rain clouds, just like Virga. That's why they look like continental Virga. So they precipitate from the North Pole. Here's how it works, Basically, during the coalescence period of our solar system, the solar system's rotating quite a bit faster then than it is now. And well, if I say I recommended to NASA that if we built a model that took us back to the coalescence period of the Earth, we would probably find, I'm picking boomy fur off my face because, you give your dog a hug and then it's like, your face is covered, especially when you have whiskers, just covered from top to bottom with boomy fur. So, and it tickles, and it makes you want to scratch your face, and you're just like the dogs. No wonder the dogs are always itching. Well, anyway, so the solar system was rotating faster. And I suggested that after describing how I would build the model, because I don't have the computer smarts to build the model or the time. I got no time. NASA can. So if they built it the way I described, then we might find that the Earth probably rotated fast enough to have one day would have been equal to approximately 8 hours. Okay, it would have probably had to have been about an 8-hour day rotation for the Earth at the time during the coalescence in order for in order for the lighter continental masses to have accumulated at the North Pole. And this North Pole accumulation is what we refer to as Pangaea. And then, of course, in addition to the North Pole accumulation of continental mass, you also have Antarctica. So Antarctica and Pangaea would have been around at the same time. One on the north, one on the south. Antarctica in the south because it's heavier. Kind of like the hot chocolate and sugar in your coffee, and it sinks to the bottom of the cup. And its galactic gravitational force sweeping around in the SMEGAWs, the supermassive electromagnetic gravity waves, that pulls that material toward the south poles of our planets, because the waves come around and they strike the south poles, and basically it creates the bottom of the planet. And I give him a little finger thingy for the bottom of the planet, because in reality the planet is like this, or in your point of view like this, right? So here's North Pole and here's the South Pole, and the waves strike this way, and then they sweep down under, which is what gives our solar system its rotation. So because of that extra gravitational force coming in at the butt end of the planet, it's pulling that material from the North Pole to the south. But at the time that coalescence would have existed, the planet would have been rotating so quickly that the North Pole, which would have been the top, had all the marshmallows and the lighter continental masses formed up at the top in one great big continental mass we call Pangaea. And then so Pangaea didn't like start at the equator and then break apart like this, and you have Europe, and then you like this, and then you have Europe, and then America. Believe it or not, they all precipitated on different sides of the planet pretty much about the same time. So it had to do with deceleration of the planet. So as the planet decelerated, the material began to spread out. As it began to spread out, centrifugal force started to force it toward the outsides of the planet, down toward the equator. Gravity pulled them down from, there's a bummy fur. Gravity pulled them down from the North Pole to the South Pole. Galactic gravity, not planetary gravity, galactic gravity. And planetary gravity basically held the greater mass, the heavier masses of the planet toward the center of the planet, which the center of the planet is the planet Earth's vortex. Okay, so planet Earth is in its own vortex. That is how it rotates, and that's the sun is responsible for the planet's rotation. And the planet rotates in a prograde direction because solar wind pressure is a stronger force than gravitational force. There you go, right? And then the sun's electromagnetic gravity waves, not supermassive, just electromagnetic gravity waves, just like our parent black hole in the galaxy, sweep around the solar system in the same direction that the sun is rotating. And it's these electromagnetic gravity waves that are rotating our planets in this orbital fashion, okay, assisted by the SMEGAWs coming from the galaxy that are rotating the sun. So it kind of gets a double effect on that. And it's because it's like the basketball rolling down the court, you know. It rolls down the court, it rolls, and where the top of the ball is going toward its direction of travel, and it's rolling that way, and that's the way it rolls around the sun, just like that, okay? And then that's how the planet rotates. The planets that don't rotate that way are just a little bit further out of reach. So you have the you have solar wind pressure is stronger than electromagnetic gravitational force, but it comes out in huge bursts, very powerful, huge bursts, and affects everything in that little huge short range zone of influence, and then it goes back to on the greater extended range of influence. You start to transition from solar wind pressure to electromagnetic gravitational force, and when you do that, the rotational directions of the planets change. And this force blasting from the sun, that solar wind pressure is like huge here, and it tapers down because the solar system is being pressed. So the Smeagol's are coming like this and striking the solar system from the back, and then the bow waves are hitting the solar system from the front, and they press the solar system into a lenticular shape. At the same time as the Smeagol's are rotating, they're pushing in. Well, that makes that sound too. I know I was there. So even Noodle thinks that. She's like, I was there too. You hear that? She said, that's what she says. Okay. Anyway. Now we're looking at the Sagittalus vortex being the oldest vortex, and then I've learned that in the same way that I learned that the continents are precipitating, I'm also learning that the equatorial vortices are actually migrating. So the vortices are migratory, while the yeah, I'd make the screen bigger, folks, but I don't feel like trying to figure out how to do that again. So I'm just like, whatever. So so you have precipitory versus migratory. So it's not migrating continents. Our continents have hardly moved at all since they precipitated. Okay, and the only really cool continent out there is Australia, and I'm still, based on the research I'm doing, every time I look at it, I'm like, yeah, Australia, just because of its alternate rotation in a direction that just doesn't seem to be, coinciding with its neighbors. It's like the opposite of. It's turbulent on almost every aspect of its perimeter, and I'm convinced it was an antipodal vortical continent created by the Guacanayabo impactor, which occurred before the South China Sea impactor struck. Don't have a clue when the Arctic impactor struck. Have no way of finding out until the Antarctica melts all the way and we can actually see the ground. Or we get somebody who gets some more powerful ground snow penetrating radar, ice penetrating radar, whatever you would call it, right? And really start scoping that stuff and coming out with some really neat appearances. I mean, you can look on the internet, and there's this rendition of a conceptual picture of what Antarctica looks like or would look like with no ice. But I don't know how correct that is, I need to find that again, because Antarctica consists of two spiral density arms. We might say two sets of spiral density arms, but really it's only two spiral density arms. And they do the S. And they cross each other. That's why it looks a little bit more rounded, because the ice makes it more round because it's at the pole, and then at the same time they're kind of like spreading out like four, octopus arms. Excuse me. Yeah, so I'm old. I can do that. I'll see. Yeah, so I'm just kind of like passing time till I get ready to get my next mug and maybe wake up a little more before I start showing people stuff. And so I can show you a sneak preview. Go right over here. So again, it's the sun that brings me to look at the Earth in a very, very different lens. And it was this particular photograph of the sun, as a matter of fact, the reappearing coronal hole by the SDO, Solar Dynamics Observatory, that suddenly struck me as, that looks like Africa. And I'm like, holy cow. So like up here would have been north and northwest Africa as it sweeps around into South Africa down here, and then you have over here you end up seeing all of these really strange subterranean ridges that are kind of like giving that sweeping from South America look. And when I was considering the possibility of rotating um, continents and things of this nature, Africa would be over here from your point of view, and South America over here, and it looked like they had one time been together like this and then pulled apart, pivotal stuff, and just straight up pulled apart, which would have implied that their vortices that they were caught in at the time that they would have done that theoretical positioning thing would be rotating in the opposite directions than they are today. So that was a tough theory to try to figure out, but then, not knowing about continental precipitation, it was just like, well, I don't know what else to say. Somehow it just looks like it should have been like that. But even if it was like landing gear and these two continents spread apart like this, why is it that the mid-Atlantic ridge is going right down between them? Okay, and then we have the plate tectonics theory of where Africa was here, Africa was over here. Africa was over here, and South America was over here. My thumbs representing the little curlicues, and they were just like, and the mid-Atlantic ridge is like this, one of those jacks, 30-ton jack, and it just and it just keeps getting farther away. Well, plate tectonic wise, that might be the case, but plate tectonics is different from vertical tectonics. And as we can see right here, vertical tectonics are quite true, and they have everything to do with DRCBs, differential rotating celestial bodies, including black holes. Okay, so now up here we have this darker area on the north of the sun, and that's like they refer to it as a coronal hole. And that darker area is dark because it's cooler, so it isn't as hot as all the brighter masses down here. And it's on the North Pole. So why is it that the North Pole is, especially in this photograph, the North Pole look to have a much larger massive area that's cold versus the South Pole? And I'm telling NASA that what we have here is we have the bow wave. The bow wave chill factor. So as the sun's being pushed forward and it's striking this resistance, that resistance becomes the bow wave of the forward forces trying to prevent the solar system from moving forward, which is why it gets smushed into a lenticular shape. And as it's doing this stuff here is cold. So it's like chilling that out. And as it chills out the North Pole, the material becomes heavier, and then you see this material begin to step over its boundaries of this nice green line right here in the Arctic vortex. And once it starts stepping over that vertical perimeter, it gets caught up in the vertical perimeters of the equatorial vortices. So it comes to the North Pole in this instance is rotating in the opposite direction of the sun, and that's just like Earth. It rotates in the opposite direction. It's like a backflow, or however you want to look at it, because the galaxy is forcing the solar system to turn this way, and it's either because the galaxy is forcing the solar system to turn this way like this so fast that it appears to us that the cores are counter-rotating, when in fact they are not counter-rotating. They're just rotating at a much, much slower rate than the outside as if there's like ball bearings inside of the sun between the corona and the core, as opposed to the center of your merry-go-round going like a centrifuge. Okay, so even though it does create its own centrifugal force. So this heavy milky stuff comes down here and spills into one of the equatorial vortices of the sun, and as it does, you have the plasma streams of the sun that we've had, that I was able to at least identify one so far, plasma stream vortex that was sitting in this belt number 1, 2, 3, 4, belt number 4, heading in the opposite direction of the sun's prograde rotation. So it's rotating, or it's traveling in a retrograde direction. That proves the DRCB theory extends from not just gas giants, but it goes to the sun and it goes to the earth. And we have the same counterflowing properties of all of these DRCBs. And as this heavy stuff gets pulled into the vortex is rotating in a specific direction. And how this happens and how you get a vortex rotating and, all these counter-rotating belts is like, I don't know. I'm really not the physicist here, and I'm not sure that our physicists would be able to replicate this yet. We will someday. If we can't do it now, we will someday. And then as you go down through here, you've got the jet stream number 1 is going prograde and forces the material this way, so it stops it from going any farther. So you have a double force. You have this jet stream, or this plasma stream, going prograde, and then you have your vortical perimeter and its rotation going in basically the same direction in belt 1. And it causes it to do this little wee, as we see here, because I'm just going with a general direction of the darkness. And you can see how this material here is actually pushing into it. So this darkness, sometimes what it does is it sinks and it travels beneath the lighter, hotter material that we see right here in the corona. And then it comes down and it reappears here, then it comes down, it dives again like a snake going into the water like this, And it's all right, like a whale. And it comes down through here. And as we can see, this is 1, 2, 3, 4. In belt 4, we end up with a kind of a very quiet area, because now you have the cold that cut this stream from flowing through. It cut it off with it. So we see, I put a white line here to show that the stream is rotating retrograde, and it basically hit a brick wall, and it comes down like this, a solar brick wall. And then the normal rotation of the vortex pushes all this stuff here. Now this material here doesn't have anywhere to go. So as it hits here, you get a bunch of little teeny weeny vortical pools that's just like, I don't know where to go. I don't know. I used to go that way, but now I can't figure out what I'm doing. And it's supposed to be going this way, so they're kind of going here where there's no pressure, and they're just floating around until this coronal hole finishes what it's doing and reopens that canal of plasma stream. Okay, and then it rotates down here, and you see it really heavy in this region, and this belt, you can see how it goes up along with our vertical rotation of this perimeter here, and it's traveling in the typical direction that a equatorial belt travels. This is the primary belt. This is the one that actually moves because of the effects that the galactic electromagnetic gravity waves have on the sun's rotation. And it's the real rotation. All the others are just fakes. They're just counter rotations to one another, to each other, right? Counter flows or back flows, whatever you want to call it. And as we see, as our tangents come together, the tangent of the east vortex and a tangent of the west vortex as they meet our primary vortex in the screen here, you have your typical prominences. Those prominences are going to be following that because you're either going to have a turbulent TT, a turbulent transient, not transient, a turbulent, what do I call that stuff? Wow, did I pull a blank or what? Tangent, turbulent, I'm still not awake. Turbulent tangent and a flowing tangent down here. So you see all these different waves and everything works together to create all this craziness in the sun. And now you apply that to the Earth. So when we apply that to the Earth, I go up here, I grab my little guy right here, oops, wrong one, and I copied that guy and then I threw him down here and then I tilted a guy negative 24 degrees to the left. And the reason I did that is because from what I could see, from learning from the way this dark coronal hole is coming up toward almost right just under the equator, not way down here, just under the equator. I'm like, well, then that might mean that South America should be curling up on inside of this vertical circle, right? If that's the case, then I need to raise South America to the point where it's more on a plane with Africa. And to do that, I had to pivot my little vertical marker here, negative 24 degrees. Then I decided that didn't work because as I actually went around Google Earth and kept taking screenshots and applying my little tool right here to each one of them on this axis, nothing added up, nothing panned out. There's absolutely no evidence whatsoever of any kind of vertical perimeter operation scoring the Earth's surface, and it was a dead end. So I'm like, well, that Africa's not a dead end. We see how I positioned it so that you have right here, you have this one section of the mid-Atlantic ridge or the planetary suture, and then it comes up here and it cuts right through Spain, separating Spain from France, right down the center of Italy. Okay, so Vesuvius has been on a frickin' hot crack for a long time. It was first on the vertical perimeter of well, okay, let me take that back because this is actually late. I figured out these vortices occurred later in history. They're not the oldest. Okay, then I repositioned it back to where north is actually oriented to where north is today. So basically, what we see here is sometime after 4.4 billion years before present, after Gokana-Yabu struck the planet and made the planet do this wild shit, and North Pacific Oceanic Impactor clobbered the planet and most of what it did is like almost completely erased, with the exception of the B2W that was left behind. And that's basically, we can blame that on the South China Sea impactor because of how it melted the planet, so to speak, at the time it impacted. Okay, now this fits perfect right here. And then I decided, well, keep going. And I came around over here, and this is what it looked like for America. And I'm like, this doesn't quite, even though the North Pole is going in the opposite direction, retrograde, and the force would have come down and brought America down this way, it just doesn't seem to explain the Caribbean and the Gulf of Mexico right here, right? So I'm just like, what is going on with this stuff? And it puts South America over here, not quite in this perimeter, and so I'm like, well, they might have happened, but it's like, it doesn't seem like something that would have been first. And then we have this guy, and I'm like, oh, check this out. Now, I made an adjustment here that may or may not agree with these three here. And I have to, well, this one, and this one, this one. This one was third. I never did get to the fourth then. And I see something here. And right here, I'm like, this is the perimeter around Africa that we established here. And then now we're looking at this one down here and over the Indian Ocean. And then I noticed, well, it seems a little high because this little niche right here looks like it might be part of this circle. And then I see like this etching going around through right through China and the Taklamakan Desert and coming around over here and coming out over here. And I'm like, I need to lower that. And when I lowered it, this is what I came up with. So this vortex is coming down here like this, and I'm just habitually rotating my cursor in a clockwise manner because I think in a clockwise manner, and not necessarily, that does not mean that this vortex was rotating clockwise, because actually I believe this vortex is a continuation of the Seychelles vortex, which is right here. And as you can see, the Seychelles vortical spiral density fracture comes around like this and goes down this way, which means the vortex was rotating in the other direction, which means it was rotating counterclockwise. And if this is a continuation of this, then that means, one, this vortex existed after the Seychelles, and the Seychelles migrated from this position here over to here, which makes the Seychelles the oldest known vortex on our planet. And I say it's the oldest known because right now the Lake Victoria vortex right here is the shit. That's the one that's really actually taking place today. So this vortical migration is a very, very, very slow process, oddly. I don't know why. But they do migrate. So we went from the Seychelles here to here, and the Seychelles moved. This is what made me decide I needed to refocus and start back further in time, making this my first vortex. And then I came up with some more interesting stuff. So this vortex is actually going in a counterclockwise manner, and so you can see how it may be partially responsible for cutting up through Australia here, pulling Australia out over here, and this material here, being that it's right on the perimeter of this particular vortex, tells me that the Philippine Islands up in here occurred sometime during this phase of vortical migration, and because the vortex is rotating up, doesn't mean that this mass of Earth right here formed in a direction of going upward. It doesn't form in a direction of going upward. It's spilling down. So it came down from like Japan and leaked down into here because of our typical precipitory method of mapping, and then come down through here and it goes into this stuff. So I don't believe the Philippines are as old as the South China Sea impactor or the Indonesian vortex. They came in at a much later date, sometime during this period. And I don't believe that India had quite been formed in this fashion at this time just yet. So we have instances where the Earth continued in a precipitory process after certain events took place, right? And the vortices, at some extent, still had an effect on the crustal layers of the planet and the continental masses. And that's the end of this one here. This is my Indo-Africa refinement. Now, the problem with me dropping this particular one down further toward the south means that it's not in line. It's taken the two other equatorial vortices down. It means it dropped down like this, so now their orientation is going to be like canted, and this particular PPT does not illustrate that. So if that's the case, then I have to take the African well, not the African precipitation, because Africa did not I don't believe Africa actually precipitated during this phase of vortical migration. It precipitated during the Seychelles, the oldest Seychelles period of marcation and whatever. And so this is just moving along and cutting the earth, and basically it could just be that it doesn't necessarily take catastrophic events for these vortices to cut and shape the earth as they on the perimeters as they rotate around the planet. It does take a catastrophic event for the lithosphere to be agitated enough to score lithosphere or lithostream scores into the, etched into the planet's surface, giving us our nice pretty little stripes like that one right there, and that one, his buddy, right down here. That's not cracks, just that it just went go, okay, I'm cracked. No, that's been etched by the lithostream that etched it at the time that it was pissed off. All right, so something pissed it off. You just don't know what or when it really occurred, right? And then that leads me to this one, and I'll start talking about this guy. Phase 1, Seychelles Vortical Migratory Period. And that's the oldest vortex right there, and this is what it looks like. And oh, by the way, very interestingly, this being the oldest vortex, we can pretty much see that north is north. So at the time when the Earth began to become solidified, we've basically been maintaining almost completely the same north polar orientation. And the lithostream scores that were etched into the planet by impactors like the Wakana-Yabo and the North Pacific Oceanic Impactor, they were etched into the planet before we started seeing the Seychelles form and carve its little messages into the surface of the Earth. So all of that horribly, really crazy stuff, all those great big impactors, well, like scientists would expect, they took place during the coalescence mostly, at the very earliest onset of the Earth's planetary evolution. So that doesn't mean we can't or won't ever be clobbered by a really large rock the size of Mount Rainier again. It just means that, you take into consideration, the biggest rock that ever clobbered the Earth was the moon. But I don't agree with the scientific theories on the moon. The moon was more like a touch and go, and not a catastrophic collision that turned the moon into splattered molten blood all over the frickin' sky, and then it just coalesced into a rock that was oddly heavier toward the Earth than outer space. I don't see that. So I look at it more like, I think that it was basically a touch and go. So it came in, goes boop, and then right off, and then it slowed down so much as it clobbered the planet and went like this that it just went, and that happened so much more earlier than any of our planet's basic continental structure that's why you don't see any effects on the surface of the Earth to suggest where the moon may have struck the Earth in that very fashion. At least, not that I can suggest so far, right? I would have to see. I would have to actually see how large the moon is And then I would have to look to see what size of the Earth could have been affected by a collision from, or a touch and go collision by the moon. And where would that be? So as you can see here, this is a lot more explanatory on how things turned out. I'll get to that later. All right. I'm going to go make my other coffee.